Hello problem solvers. So here is an inequality. You can try first and you will quickly realize its difficulty. Please have a go. So we are given that some real numbers that is greater than or equal to 1, and we want to prove this. Again, you have fractions, so that means you can first try to apply Tito's lemma. Okay, please try that. It won't work, but please try. Okay, that's how you realize. Well, if you try that and you realize, let me just quickly show it to you. So if you just try Tito's lemma, you get the sum of these, which is n plus the sum of the ri's. Okay, and we will hope the result will be still greater than this product. Okay, this is n squared. Okay, if you so this becomes n squared. You cross out this n. I have an n left. So you just bring this up. Cancel. And so you're left with AMGM. But in the reverse order, right? This is the GM. Bring this n to here. This is the AM. In the reverse order. So you know this inequality. You see? So left hand side is here. Okay. Right hand side is somewhere here. Okay, this is vertical. The bigger is at the top. Okay, so we want to prove that this is higher than this. But using Tito's lemma, we from here to here, we jump to here. This, let's say this is xe. We jump to here. That's too low. Okay. So when we talk about inequality, we have a thing called sharpness of an inequality. Okay, the sharper it is, that means the smaller jump it is. Okay, it just decrease it a little, right? When you apply this inequality, the great thing is that it simplifies the expression a lot, right? From n fractions become one fraction, but also it decreases its value. Okay, and in this case decreases too much. Okay, and the question asks us to prove a tighter bound. Okay, so just applying Tito's lemma, which is Cauchy's inequality. Okay, that is not sharp enough. Whenever you encounter this situation, okay, that means you need to work much more, and that's how you know this is not an easy inequality. But if you think about it, if you tried well, there are fractions, and we tried Tito's lemma, it didn't work. What's the next thing to try? Well, you have fractions, so not many inequality involve fractions, but one common, let's say, general inequality is the Jensen's inequality, right? So please look it up. I'm too lazy to put it up here. Actually, Jensen's doesn't work as well, but let's try. Let's try to see why it didn't work. So you see, if you know Jensen's inequality, so on the left hand side, this is just the sum of FRI, where my f is this function, right? If you bring this n here, that's just like the fh of the f values. Okay. So, and the right hand side is this. Let me just keep writing this. Sorry. So this will be n of f of g. Let's say gn, where gn is the nth root of the power. Okay. So in other words, I can write it this way. Okay. But what Jensen gives you is, Jensen says this is at least an. Again, an is too rough. Gn is here. Okay, so same scenario as before. Okay, you can verify that, where an is the fh of the Ri. You can verify that. So this just calls for, well, the Jensen didn't work, but this approach seems like we are in the right direction, because we can neatly write everything as an f. What's next to try? Well, basically that means you can't apply well-known inequality. Basically, well, of course, if you know some other, maybe you know another inequality, you can apply here, but I don't know. Okay, of the ones that I know, I cannot apply here and it will work. So basically that means you're left on your own. You need to prove the inequality just without any help, and that's what we'll do. Standard mathematical induction works from statement Pn to statement Pn plus 1, right? Or you can do strong induction, whatever. Usually the traditional way is just go from one step. But the proof for AMGM using mathematical induction, it doesn't go this way. It goes from n to 2n and then 4n and all the way. Okay, and then you just need to use, so then you go backward, right, from, because once you know that the statement for 2n works, then if it is easy to go back, it doesn't have to be 2n to 2n minus 1. Just in any case, whenever you see the statement from pk plus 1 can work for pk, so that means if I assume this is true, I can easily derive this. Then you know you should try mathematical induction in this way. Okay. So you see, so let me maybe explain clearly. So I'm going to prove that the statement is true for n, for 2, 4, 8, 16, for all powers of 2. Okay, and then I go back. For example, I know P32 is true. Then I can apply this apply this fact. I know this is true. I apply this fact for 31 numbers, and it will work. And then I apply this statement to prove this. So you go backward. Okay. And one thing to try to see if we can do this. If you can do this easily, you can. If you know this statement is true, you can prove this statement is true easily. Then you should go this route, because usually proving, so going from n to 2n is quite simple usually. Okay, so let's just prove this part first. So, but this is not what you should do on your exam. Okay, let's say step 2. Let's say part 2. Okay, let's do part 2 first, because that's what you should try first before you know it will work. You should try to see if this works. Oh, if it works, then probably this will work. Then you just try out. Okay. Maybe just claim 1. Claim 1. So let's say this statement, I call this statement, okay, Pn. Okay. Claim 1 is that if Pn plus 1 is true, then Pn is true. Okay, let's prove that. So this means that for any n plus 1 real numbers, this will work. Okay, for Pn plus 1 means for any R1 to Rn plus 1. Okay, this is at least n plus 1, n plus 1 product plus 1. Okay, now we want to prove Pn, which is for any n real numbers. So let's say we have these n real numbers. Okay, then I'm going to set R1 to be x1 all the way to Rn to be xn. Okay, but what should Rn plus 1 be? Well, we want to make it work, so just try it out. So you see the Pn, the left hand side looks like this, right? Sum of 1 plus xi, right? But I'm going to use my induction hypothesis. Okay, so in my induction hypothesis, I have one extra term, which is, and I'm allowed to, I can choose any real number here. And on the right hand side, I have this, the product of the R's. Of course, if this number is equal to this number, then I can just subtract. Okay, this thing is equal to, if this number is equal to this whole number, I can just subtract. Okay, and then I have n over 1 plus this, right? So you just set, you just solve for it. So let's say I want this one to be equal to product of this. Okay, so that means Rn plus 1, n plus 1, R1 to to Rn plus 1. So that means my Rn plus 1 should cancel out nth power, should be the nth root of this. Okay, so that's what you will do. You set Rn plus 1 to be the nth root. Okay, then in my p plus 1 statement, okay, I will have I will have 1 plus R1 all the way plus 1. Okay, but I just set Rn plus 1 so that this is equal to this. So at the bottom, well, I just set Rn plus 1 so that this is equal to this. So this is just Rn plus 1. Okay, and so this is one copy of this. This is n plus 1 copies of this, and you can just subtract to get n copies of this. But we also know that Rn plus 1 is this. Oops. Okay. And so, I should have write xe in terms instead of r, but let's just call this out. Anyway, so that shows that if assuming the Pn plus 1 statement is true, you can prove the Pn statement is true. You see, this is the Pn statement. Okay, so I've just proved that if Pn plus 1 is true, then Pn is true. Okay, claim 2. So I just verify that this part works. Let's try this part. Let's see if this part works. So claim 2 is that if Pn is true, then P2n is true. So let's look at the P2n statement. Okay, you have 1 all the way to Rn and all the way to R2n. I want to prove that this, let's not wait. I want to prove that this is 2n, 2n. Okay, so now we this is still, I'm still testing. I'm not sure if the solution works. So that's what I do. I try to prove the 2n statement, and if it works, then that will become my proof. So I have n numbers here, n numbers here. So of course you will apply the Pn statement here. Okay, and so you are left with and n numbers here. Apply the Pn for these n numbers, and you have Okay, and it remains to show that this part is bigger than this part. Okay, it remains to show this. Okay, let's simplify. So let's cross out the n, and this is, let's just call it x. Let's just call this y. Then what is this? You see, x is this. X is the product from 1 to n, nth root. If I do a square root again, this is product of 1 to n with root, with the 2nth root. Okay, but you see, this is somewhere from R1 to Rn, 2nth root, so that tells me this should be square root x times y. Okay, I just simplified. I just call this x, call this y. Okay, and you can see that this is just the statement for two numbers. This is just P2. This is just P2. We haven't proved it. Okay. So let's just say this is the this is the P2 statement, which will follow from claim 3. Okay, so the claim 3, let's prove that P2 is true. Okay, let's try to prove that. Okay, you just need to prove this statement. Okay, well, usually I don't like square root, so usually I'll just let's say a is square root x, b is square root y, then I have okay. Let's just, because you only have a few terms, and let's just multiply everything everywhere. Let's just do expansion, simple expansion. Okay, so AB3 oops, did something wrong. This should be 1. Okay, and let's cross things out. Okay, I'm left with so let's make it okay. And this in itself is not easy to prove. That's you can't really apply AMGM here. Well, maybe some clever combination you can do that, but there are only a few terms, so a good strategy would be just factoring. So I'm going to take this term and this term. So I have AB squared B minus A. Okay, I take this term minus this term, and I do this term minus this term. That would be A squared B A minus B. Okay, and then this term minus this term, B minus A, and then I do this term minus this term. That would be B A minus B. And so you see, we can factor out A minus B. Let's just factor A minus B. So I'm left with A squared B, and then minus this, because this is B minus A, minus this. And then B minus A. And you can further factor. So this would be AB A minus B minus A minus B. Okay, so you can further factor, and you're left with AB minus 1. And if you substitute everything back, you get x square root x squared y xy minus 1. Okay, and you see xy should be at least 1, and indeed it is. Okay, the numbers are that they should be greater than or equal to 1. So the product will be greater than or equal to 1. Multiply this, and everything can be reversed, and we have proved that the P2 statement is true. Okay, so, and that is our mathematical induction, right? Because the base case is P2 is true. Claim 3. Induction step. From Pn, we prove it to 2n. That is true. Proven by claim 2. Okay. And finally, walking backward. Right? If Pn plus 1 is true, Pn is true. That is claim 1. Okay, so by the mathematical induction, Pn is true for all n. Okay, so this is not the standard form of mathematical induction. You go to 2n first, and then you go back. And that concludes the proof of this problem. And as you can see, It's not. Well, if you have lots of experience solving inequality, it is not that hard to come up with this. Okay. Yeah. So I would say this is the difficulty would be about difficulty 7 or 8. Let's say 7. And yeah, it should be. And in this case, the character is Kakashi. Okay. Okay. Thank you very much. Thank you for watching.